Well, thanks a lot, Brandon. I hope everybody is back ready to go. So routing geometry is a new feature that got added this past year. The presentation on it's pretty short, so we'll should have some nice time for a demo at the end and certainly for questions along the way. So historically, OpenVSP components, the different geometry things, are each defined independently. Each, whether it's a pod or a wing or whatever it is, it's its own thing with its own parameters and its own position, and it's not dependent on the other parameters. Um, and so there's some exceptions. We can use attachment to build positional relationships between components. So attachment doesn't change the shape of a component, but it changes its position and orientation relative to its parent. We have conformal components. We haven't talked about those yet, but a conformal component builds its shape off of its parent component. So typically you'll do an offset thickness. So maybe you want to model a fuel tank within a wing. And so those use the parent shape, but they use directly the immediate parent's shape. And then there's also what we call subsurfaces, which is the ability to sort of draw a box or a line or some curve on another surface. So you can draw a control surface on a wing or draw a window on a fuselage. And therefore, obviously, the window shape is dependent on the shape of the fuselage. But in all these cases, the dependence follows the parent-child lines. And what I mean by that, when we look at a model in the Geom browser, we see this hierarchy where as we go down the tree, in this case, the fuselage of this model has a child of the pilot in the cargo bay, and also the horizontal tail and the wing. The horizontal tail has the vertical tail upper and lower as children. The wing pivot has the wing as a child, and then a cell tilt, and all these all the way down. And so all of these different components are parent children. And so the way attachment is identified is this double bold line indicates that the wing is, well, forced attached to the wing pivot, or the vertical tail is attached to the horizontal tail. So here we represent attachment with these double bold lines. But the way information works in an update of VSP is, for example, when you update the fuselage, then when VSP is done updating the fuselage, it then updates all of fuselage's children. And it checks to see if they need an update. It obviously stops if things don't need to be updated anymore. But we follow this hierarchy from parent to child in the update process. And that was a fundamental thing that was going on. Now, what this means is that, for example, you can't have a spinner over here. Well, no, that's not a good example. Let's say, no, we can't have the spinner and have the spinner's position or parameters depend on the upper part of the vertical tail, because it's not in that same hierarchy. You can't have the spinner and tell it to be symmetrical about the upper part of the vertical tail because of the way this model is constructed. And this limitation hasn't really been a problem so far, and VSP gets a lot of efficiency out of this approach. And so so that's been a fundamental design decision. What we're talking about now, routing geometry, kind of breaks that, in that we needed to find a different way. And you'll notice in this model, the routing geometry is not a child of anything else. And yet we'll talk about what it does and how it works. It does depend on lots of these other components. So the routing geometry is kind of breaking the rules of how OpenVSP updates things. And it really only matters right now for routing geometry, but it might matter more for other things in the future. So we'll have to keep an eye out to see what this means. So the use case of routing geometry, what I mean is we've got this sort of generic tilt rotor model here on the left that looks like a V22, but it isn't really a V22. And what you'll see, it's a little tough to see, but in here there's this black line that starts at one of the spinners and runs back the nacelle to the tip of the wing, to the root of the wing, down into the fuselage, and then back to the aft fuselage. And I've isolated just that line over here on the right. And so that is this routing geometry. This, zigzag line can be used to represent lots of things in an aircraft that are routed through the aircraft. So that includes, obviously, things like hydraulics, pneumatics, shafts, electrical, cables, push rods, fuel lines, any of these kinds of systems that are routed through a geometry, through an aircraft, is the use case for routing geometry. And back to that update hierarchy, a routing geometry can depend on multiple components, so it's not just single dependence, but it can also depend on components that are not its ancestors. So we have to break those rules. And in this case, you'll see that the routing geometry is attached to the spinner and attached to the nacelle and then to the wing and the wing root and then into the fuselage. So that routing geometry actually depends on half the components in this model. So it has multiple components that it depends on, and these components are not all in a linear, clean hierarchy tree. They're located all over, or potentially they can be located all over this hierarchy. There are limitations right now, and we may continue to improve routing geometry going forward. But right now, it is not a full surface. It's not an elaborate geometry. It is just a line representation. All of the joints, the corners, are sharp corners. So we're specifying it as like a 3D polyline. And we don't have the ability to put in a radius or a blend right now. And there's no cross-section shape. It doesn't have any area or any shape to it other than it's just a line. It's not a full first-class component. I don't generate a Bezier surface of this, and it's ignored by most analyses in VSP. It's also ignored by most exports. So if you build a routing geometry in VSP and you export to STEP and you take that into CAD, it's not going to go with it. Right now, it just only exists in VSP. And then back to that update hierarchy, you can't attach something to a routing geom. You can imagine that if somebody routed something through a model and then they attach something to the routing geom, that would create the potential for a circular loop. And infinite loops are bad. So to prevent that, we just made it so that you can't actually attach something to the routing. You can only attach the routing to other things. And these are the current limitations. That's just the ground rules that you have to work with if you want to use this. But what it does give you the ability is to visualize this route, whatever this is, whether it's a fuel line or hydraulic or a shaft. You can visualize what it looks like through the aircraft, and it'll also calculate the length. And in the current example, this is actually one routing component, which was built up on the right wing, and then it was mirrored using symmetry to the left wing. Down the center line, they're coincident, so you can't see them separate. But when it calculates the length, it calculates the length of just the first copy. And then if there's 2 symmetrical copies or 3 or 5 or however many symmetrical copies there are in your model, it'll then take that length of 1 and multiply it by the number of symmetry to give you the total length, if that's what you need. And so for most of these things, say it's wiring, you could use this to do a hand calculation of the mass of that wire, because you would know that for whatever gauge wiring you have and however many strands, you would be able to say, okay, my wiring weighs this much per foot or this much per inch or this much per meter. And you'd be able to take that length calculation and get at least a first cut mass properties calculation. If it's pneumatics and you're doing a loss calculation, you'd know the length of that length, so you'd be able to do that loss calculation. Again, if it's wiring and you're doing a resistance calculation, you know the gauge of your wire, you'd be able to then figure out the resistance of that wire. So all those analyses start with length, and we're really just sort of giving you enough to get started. Okay. So here's the routing geometry GUI. It's a regular GUI. It's a regular geom in terms of the general and X-form and mass tabs, although a lot of that stuff doesn't work in the traditional way. But really everything happens under the design tab. And Up here at the top of the design tab, you have a GUI for interacting with each of these points along the polyline. So I'll call that the routing point chooser. And here I didn't give them names, but you can see each one is attached to a different parent into that symmetrical copy. And you also have these ordering controls. So if you need to change the order of points, you can click on one of these and move it up and down in the ordering. We have a bunch of buttons for point management, so you can add and insert, delete, or reset points, and I'll demo all of those in a moment. You can also name each point, which I was too lazy to do here, but you can name each point so that you can know that, the endpoint is a battery terminal and the other endpoint is the motor, and you can name the waypoints to make it easier to work with your model. Then you can control the parentage. Now, when we build this, you can actually do it just by clicking on the model, and so parentage will be set automatically. But if you want to come in and change it later, you can come in here to these menus and you can change what a component is attached to, or what one of these waypoints in the routing point is attached to. Then you have full control over the attachment. So Brandon talked about attachment in the earlier demo, but you can attach a routing point in UW, you can attach it in RST, you can attach it in LMN, dimensionally or non-dimensionally. On a wing, you can use ADA. So you have all of these different ways of attaching it that should match, your use case. When you initially attach things by clicking on points, and I'll demo this in a minute, the default is everything attaches in UW, so it'll be on the surface. And then if you want it to be within the volume of something, you can then change it from UW to RST or LMN, and then adjust that T component to put it somewhere in the middle. You don't just attach it, you can actually then offset it. So when you attach something in, UV, if you then want to offset it, say in the normal direction to the skin at that local UV, you can come in and dial in a delta for that offset. So you have a tremendous amount of control of where the points are, either on a surface within a volume or offset in that way. And then down at the bottom is that length calculation I was talking about, where length is the length of the single copy, in this case 662, and the symmetrical length then gets both halves because we're multiplying this one by 2. And that's all for the slides. I can take questions in the YouTube chat while I fire up a demo to just show you guys how this works in practice. And some of the things I'll be demoing later in the workshop are not yet publicly released, but routing geometry is. So you can do this in VSP that you've downloaded. So to start with, let me just add a pod as just a quick demo, and I'll move that out and I'll make a symmetrical copy. So we have now 2 pods here. And then let's just add a wing, and let's move that up in Z, and we'll move it aft a little bit like that. So here's, just a very, who knows what this is? Maybe those are the floats on an airplane, and we want to, build up some sort of a truss framework. Why not? So we can come in and, these two are related to each other. We could even come in and we can attach them. That doesn't matter. But independent of that, we'll come and we'll add a routing geom. So that's down the last one of these capitalized built-in components. And so we'll add that routing geom, and here it is. We'll come over to the design tab, and we can come and we can add a single routing point, right? There's nothing there yet. We need to add a point, and presumably we'll need more than one. So we might go straight to add multiple. And so when we add multiple, you'll see all these green dots appear, and these are the points that we can choose to route between. So we'll start and we'll route between this point here and up to here on the wing. We zoom in a little bit to say there on the wing, and we'll go back down to our fuselage or our float, and we'll click there, and then we'll go up again to the wing, and we'll click here. So there we just routed and we clicked 3 points. We're now still dangling around to add more, but I can just come over here and click stop adding, and I'm done. And so right there, I've created a routing geometry between 1, 2, 3, 4 points on this wing. And the great thing is that if I come in here to the pod and I move that pod around, you'll see the routing geometry is updated on the fly, where I can come into that wing, and I can come in and I can change the sweep angle on that wing, and I can do anything you want. I can update the tip chord on that wing, and everything's updating on the fly in that routing geometry. And if I come back, you'll see we've calculated that the length of this is 26.77 units. If we want to turn on the symmetry of it, all we have to do is come up here and turn on the symmetry of that routing geometry. In this case, the symmetry is applied somewhere of its hierarchy. It's a base model, so we can really only be symmetrical about the global origin. And that gives us two of these things, so we can come back over to the length, and we'll see that their total length is double, as we would expect. Now, if we want, we can come in to any of these points, and we can change them. We'll come to the second point, which you'll see it's highlighted with this blue dot right up here. And if we don't like the way that is the place where that is attached, you can see we can come in and we can dial, leaving it in UV or UW. I can move that point of where it's attached, and I can move that along the surface, because that's what UW does. But I can also come in and say, you know what, I want to change this to, say, eta mn, and it stays in the same place because we're calculating the equivalent coordinates in all these different systems on the fly. And so eta mn, eta is our span-wise coordinate, m is our chord-wise coordinate, and then n is our thickness coordinate through the volume. And so if we want that in the middle, we can just change that to 0.5. And now you'll see that as I move that in the m direction, which is the chord-wise direction, we're just moving there through the center of that wing and thickness along the chord, and eta is along the span. So we can change how that is done. We then have the ability to do this kind of, a delta in the coordinate system, which allows us to come in and we can then offset in each of these axes. You'll notice that this coordinate point has a triad. A red, green, blue triad is shown at that point, which is where the eta mn is attached. Let me change it back to 0 to convince you of that. So as I move this around, you'll notice the triad is moving with it. That triad tells you that local XYZ coordinate system that it's going to use if we put in some sort of a delta. And so, we can move that along that local XYZ, or if we come back, you'll notice that when I switched to absolute, now we're in global XYZ instead of relative. So relative is actually moving in model units, but in the unit vector directions of eta mn, taken instantaneously at that point. Whereas if we go to absolute, now we're just moving in global XYZ from that point. So relative allows us to, say from eta mn, it makes a lot more sense. Let's say if we go back to UV, now we're on the surface, and let me move that so that we're somewhere up around the leading edge. You'll see that normal vector, that z vector, the blue one, red, green, blue, the blue one is orthogonal to the surface there. So if we come in and we say, okay, we want to be at that point, but then we want to offset, a certain distance off of the surface in the local normal direction, that's what that delta is for. Okay, so you see we have a lot of capability to move those points around. If we come up and we say, you know what, I want to change what that was connected to, I can either come back to the parent and I can say, I want to instead connect that to, the pod or to the wing. I can change from surface 0 to surface 1. So that's the symmetrical copy we can attach over there. So we can change that, or we can come in and we can just say reset point. So if we're on one point, we can just say reset. It'll give us the green dots. Now we come back and we can pick where do we want to attach it to. So now let's say, we wanted to attach it out there, and we've recalculated everything. In addition to add, I added these initially, but if I want to add more, that's going to add them at the end. So it'll add it at the very end of the list, whether we add one or whether we add multiple. We can also insert. And so what insert will do is whichever one is selected, it will insert before that point. So if we have number 2 selected right now, and we say insert, we're going to be able to then insert between the first and second point. So we can do that and say attach down there. So now we have those. I can, of course, delete that point because that was crazy. We don't want that. So we can delete, we can insert multiple. We can also reorder them. So right now, this point is number 2, but I can reorder that to say be number 3 or number 4, and you can change whatever that order is, and the lines all update on the fly. I think that that's most of the features demonstrated on a simple model. Let me open up that tilt wing just so that we can see something a little bit more realistic. Sorry, tilt rotor, not tilt wing. So here we go, and I will shade it. So here's that tilt rotor model, and I'll be using this tilt rotor model later for more demos. But here's the routing. We have, 7 points that go from here on the spinner all the way back. And the nice thing I've done about this is when I'm going through a joint, through a hinge, I've actually attached them to the hinge. So you'll notice this one is attached to the nacelle tilt, and this one is attached to the wing pivot. And the reason that's nice is I can come in here, for example, to the nacelle tilt, and I can rotate that nacelle, and I can dial that in. And because the routing geometry is going through that point as it goes through the articulation, in this case, the length of that routing geometry stays constant because it's going through that point. Whereas if I drew it to some other point and I skipped that, it would actually stretch. It would either stretch or shrink as you rotate things through that articulation. So you just have to think about how your model is built. And of course, we also in this one, we have the wing pivoting. And I've set up symmetry in this case. Well, there's something that looks ridiculous. I've built the symmetry in this case about the global XYZ axis, which means that the second routing geometry is reflected over and about XYZ, so it's absurd when it rotates. What I should have done is instead built it symmetrical about the wing or about the wing pivot. Now I should actually be able to change this. So let's see what we can do, because currently in VSP we have the ability, and Tim will talk about this later, to change the parent-child relationship without destroying or cutting and pasting. And we can do that with these 2 buttons. Again, Tim will talk about this later. But if I change this parentage to inside, it'll become a child of the wing pivot. So we'll do that once. And so now it's a child of the wing pivot. And if we look at symmetry, is symmetrical about that. I'm sorry, now it's a child of the fuselage. So let's make it again. Now it's a child of the wing pivot. Let's see, let's move that up just so that, nope, I was wrong. That made it a child of the horizontal tail. So let's promote that. Okay, now we're there. Now we're there. Okay, now we're a child of the wing pivot. And we want its symmetry to be, and I've got this all borked. We want its symmetry to be about the wing pivot. I don't know why the origin one is so messed up. This may be a bug that I need to go fix, folks. Yeah, I'm gonna back up on this and say that I need to go sort this out and get the positioning right on this one. Let's just change this back and pretend like this didn't happen for a minute. So let me sort that out. But I think in general, you guys get the ideas of routing geom and its use case and what you can do with it. Any questions on that?
So we haven't been seeing a whole lot of activity in the chat over the last one. Good walkthrough on this. Really interesting feature, and given all of the changes that you had to make under the hood to even make this feasible, I think it shows some interesting promise for things down the road. But yeah, I mean, this is a brand new thing, and so it's still a baby feature, but still really, really cool. So I appreciate the walkthrough and the demo, Rob.
My pleasure. My pleasure.
So I don't know if you can see it. Brian just asked if there is any reporting for the geometry, like mass properties. Is there a way to export a CSV of all routing lengths and lines and how they're attached or placed?
Yeah, I see that question. So right now the length is not hooked up into the mass properties calculation built into VSP. It's completely independent right now because this feature was just added on a pretty quick schedule. You can, through the API, access the XYZ global coordinates of all the routing points. So there isn't an export like a CSV or another manual export of that at this time. But if you need that information, you can, write a quick Angel script or write a Python script and, update your model, and then you can dump out the XYZ coordinates of all those routing points, and then you can do your own, calculations from there.